All right, so the first thing you're going to do when you have a problem like this is you're going to write the law of conservation of energy that I've changed to include the fact that work could be involved in the problem. So it's like the combination of the law of conservation of energy and the work energy transfer theorem. So you're going to begin with KO plus UO plus W equals KF plus UF. So if I read the problem, it says a cyclist approaches the bottom of a gradual hill at a speed of 11 meters per second. The hill is 5 meters high, and the cyclist estimates that he is going fast enough to coast up and over it without pedaling. So as far as the picture goes, I probably have it so it looks like this, and go up and over it. So at one point, he's going to be down here, and then this is going to be where he ends up. So this would be his original position, and this would be his final position. So when he's down here at the bottom, he's at the low point. So what can I cancel out in this equation? UO, because that's the low point. He is moving when he's here because he's approaching with a speed. When he's here, he's approaching with a speed of 11 meters per second, so he does have kinetic energy. But it does say ignoring air resistance and friction, so what else can we cancel out? W. So we cancel out W. Now remember, some of these problems might have two W's. There might be a positive work that's increasing the energy, and there might be the negative work due to like friction air resistance that the person has to overcome. So you could have a problem where a W1 and a W2. Also, though, remember if it's a negative, if it's work due to friction or air resistance, at some point you have to make that a negative. You can make it a negative right away or wait till the end, but don't forget to do it. I actually forgot to do it earlier today, and we got the wrong answer. And I knew as soon as I got the answer, because I knew the answer was for problem 23. The answer had to be bigger than 100 meters, because that's how high the rocket went up with air resistance. So you know it's going to go higher without air resistance. And we got a smaller answer because I didn't make it a negative work. All right, so let's see. Now it says the hill is 5 meters high. So we know right here that's 5 meters high. And so we know that it's going to have potential energy at the end. And it doesn't mean that the person has to run out of speed there. We want to figure out whether he will have a speed when he gets up to the top of the hill. So here's the equation. Nothing else cancels out. Notice that all of the facts are given in terms of like height and velocity. So that means that I'm not going to leave them as K and U. I'm going to replace them with, the breakdown of each one of these energies. So I'm going to have 1/2 MVO squared equals 1/2 MVF squared plus mg times the final height. So there's my equation. The physics is over with. Now it's just algebra. The unknown is find the speed with which the cyclist crests the hill. So we're looking for that. So all I have to do is rearrange this equation to get that by itself. Also notice that the mass wasn't given in the problem, and we don't need the mass because the mass is in every term that we have here. So I can cancel out the mass from all three. I now want to get rid of fractions. So I'm going to get VO squared equals VF squared plus 2 GHF. Since the unknown in the problem is the VF, I'm going to move this to the other side and then take the square root, and that will get me VF. So when we've done all of that, we're going to get VF is going to equal VO squared minus 2 GHF, and that's going to be the square root of that. And that'll get us the final velocity for this problem. So you're probably going to see one like this, something like this on the test. So let's see. So final velocity is going to equal the square root of VO squared minus 2GH. Always put your parentheses in that you're just going to be plugging in the numbers in. And I notice how this right here is bigger than that because I need some room so I can write in the number and the unit. If you have if you don't have a unit in there or you have the wrong unit, if you've noticed on my test, you're going to take I'll take off a point. If you don't have the unit that you should get, like if I have, let's say for G, if I put meters per second instead of meters per second squared, then I can't get meters per second for my answer. That has to be in meters per second squared to get the right units. So plugging in the original velocity was 11 meters per second. Gravity is 9.8 meters per second squared. And the height is 5 meters. And if you solve that, notice that the second term here is going to reduce. If this wasn't there, then if I take the square root of 11 squared, I'd get 11 squared. So I would literally get the same answer for the final velocity as the original. This is what adjusts it so that because I'm going uphill, I'm losing energy. I'm losing some of the kinetic energy I have, and it's becoming potential. So what do you get there? Hopefully you get a positive number under the square root, because if you don't, then that means either the hill is too high or I wasn't going at a fast enough speed when I got to the hill in order to get up over it. 10. Is it? I don't know. Did you take the square root? Because I think.
Yeah, I did. Yesterday, so the answer was
4.8. Okay, yeah, 100. What did you say it was?
109.5.
Yeah, that can't possibly be the answer because it started at 11. It's definitely going to be less than that. So you said what did you say? I said it would be 4 point. What was it? 4.80 meters per second. And let me put that in here. So you've got 11 squared minus 2 times 9.8 times 5 equals square root of the answer, and you get 4.795. So 4.80, this is the answer.